Hey everyone, today we are going to go ahead and implement the vision transformer. So I already expect that you know a little bit about transformers, the attention mechanism, that sort of stuff's just a little bit of a prerequisite going into this video. If you don't know, then just go ahead and take a look at one of my earlier videos. I'll link it down below and in one of the cards above. So you can see exactly how the attention mechanism works. Today, we won't be looking at the attention mechanism specifically, just how do we use transformers to solve a vision problem. And what I also want to do here is this is going to be a full reproduction script of the vision transformer on the ImageNet dataset. This is especially important, and we're going to kind of see later that training a vision transformer from scratch is actually not as simple as it looks. It's not just like oh, just go ahead and train it and you'll get great results, even on a big data set. And we'll kind of explore that later and what are some of the methods we use to deal with that. For now, though, let's go ahead and just talk about the general principle of what a vision transformer is doing. In a vision transformer, we kind of have, actually in transformers in general, transformers are built to solve a sequence problem. The entire purpose of them is to learn, in the case of tokens or in sentences, how is every single word related to every other word, and how are they positionally related to each other, and all that sort of stuff. And this is very obvious in the case of language, because language by itself is a sequence, right? So there's really no problem there. On the other hand, in the vision transformer, or if we want to apply the transformer to a vision task, what is the sequence? What we have is an image, right? And an image doesn't have an inherent sequence to it. Now, there are a couple ways that you could have done this, but the way that the vision transformer folks ended up implementing it was basically the easiest way possible. What if we take a picture, cut it up into some patches, like you see here, just cut it up into some patches, and then treat the patches like a sequence of image patches. And that was basically the key novelty of the vision transformer paper. This entire module, everything you see here, is only a couple lines of code. So really the vision transformer part of this implementation will go by pretty quickly. And that'll be the patch embedding module, the thing that takes a picture and then cuts it up and places it into a sequence of quote unquote embeddings, right? Embedding flattened patches. So now that we have that, after that we have the transformer encoder. This transformer encoder is identical to every other one that we've implemented. So we've done Roberta so far. So the code that we'll write for the transformer encoder is going to be about 90% the same as what we had done in Roberta. There's obviously no masking strategy or anything like that, but so if you've seen Roberta, then you should be more familiar when we get to that part. We also have this additional thing called the CLS token that we add on, and we'll talk exactly what that is, about what that is, once we actually get to it. But there's kind of a couple reasons I wanted to implement the vision transformer. There's already videos on this on YouTube, so really this isn't adding much extra information to what's already out there. But I did want to talk about two key things. Number one, vision transformers are very hard to train on large data sets because they require heavy amounts of data augmentation, and we're going to take a look at that later. What's more interesting, though, is trying to train a vision transformer in an unsupervised fashion. And so really this video acts as a prerequisite to the masked autoencoder paper that's going to come next, the implementation, a full reproduction script of the masked autoencoder. Both of these implementations are already in my GitHub, so you can take a look at them. But yeah, this is basically a prerequisite for the actual architecture that I'm more interested in kind of talking about. So let's go ahead and get started here. We're just going to go ahead and implement the model, right? We're not going to worry too much about it. And then we're going to spend a little bit of time talking about the training script because that's where it's a little bit more interesting, actually. So let's go ahead and start. So all we're going to need is our torch, torch.nn, and nn as nn. And then we're going to need import torch.nn.functional as f, just like that. And so like we know, the transformer has a couple of different parts. The first one that we need to work on, right, is our transformation from these from our image to a bunch of patches, right? Linear projection of flattened patches. So to do this, instead of looking at this figure over and over again, I actually have a notebook. This notebook goes into a little bit more detail if you are more unsure about some of the inner workings of transformers. So we talk about multi-head attention and all that stuff. I'm going to assume a little bit of this is assumed knowledge already, but again, just go take a look at my attention video if you want more details on this. For now though, let's just go ahead and get started right here. Our patch embedding module, which is basically the entire novelty of the paper, is to take a picture, cut it up into patches, and then embed them, right? Project them to some embedding dimension that we want and treat them kind of like a sequence of patches, if you want to call it that way. Now, one thing you have to determine ahead of time is what is the patch size. So we have a picture here, and the pictures we'll be working with are going to be 224 by 224. So they're going to be a 224 by 224 resolution image. We'll take that image and cut them up into patches of size 16 by 16, and that's the base vision transformer. It uses 16 by 16 patches. Obviously, the smaller the patch, the more patches you'll end up having in the end, right? So it's kind of a, that's the trade-off. How many patches do you want? We'll talk about practically why the vision transformer is better than a convolutional neural networks. It's not always better, but there are some instances where it's better. There's kind of a trade-off. Some have benefits over the other ones. And so we're going to talk about that a little bit later. But for now, let's just go ahead and get started by implementing our patch embeddings. So to implement the patch embed, we're going to do class patch embed nn.module nn.module. So yes, so we can do our init self, and we're just going to provide it the stuff that we know. So we know the image size is going to be 224, right? 224 by 224 images. We're going to use a patch size of 16. That's pretty standard for a base vision transformer, but larger vision transformers typically use smaller patch sizes, but this should be fine for now. We'll have our in channels, right? In chans. This is how many input channels are going into our model. RGB images have 3 channels. And then the embed dim that we want is going to be 768, right? Just like that. And let's go ahead and create some fake data so we can actually do this. So if name equals main, right, what we're going to do is rand is torch.randn, and we're going to say, let's say batch size of 4, in number of channels is 3, and then 224 by 224. So this is our typical image shape. And so then we'll have our patch embedding module, patch embed, and we will pass in rand, just like that. So let's go ahead and write our forward method, def forward self x, and we're going to pass right here. There we go. All right, so how do we cut our picture up into patches? And there's actually a couple ways we can do this. We could have done patchify, right? So we could there's literally a function called patchify. It's like a package. It takes a NumPy array and cuts it up into patches exactly as the visual described, right? We're just going to take our picture and cut them up into patches. One thing to keep in mind here, though, is notice that these patches are not overlapping. They could have been overlapping, but in the case of the vision transformer, they decide not to do overlapping patches. But if we want to take a picture and cut it up into patches, don't we already have a mechanism of doing that in a really easy way? And we do, right? That's the convolution. So if you remember again, a convolution is just a sliding filter, right? Just a sliding filter. And what we can do is, if we want a patch size of 16, right? 16 by 16 patches, why not have a kernel of 16 by 16? So a kernel size of 16 by 16. And then we have to deal with our stride. So if our stride was just 1, then each time we scan our image with our filter, right, convolve our image with our filter, each part of the image would be overlapping, which wouldn't really work out. So what if we just picked a stride of 16 as well? So all that's happening is we have a 16 by 16 kernel, and then what we're going to do is move over by 16 every single time. That way there's no overlapping happening between your different extractions, right? So that's the key idea. You can obviously write a patchify function, and that would work just as well, right? It wouldn't really make a difference. But we're going to stick to kind of the typical implementation that you'll see online. So I did mention, right? So vision transformers, the entire point of them is, can we do vision problems without convolutions? And we're immediately breaking our rule here because we do have this convolution, but this convolution is mostly just to be able to use GPU acceleration to do the patchification task without kind of all the extra headroom of like doing it in NumPy first and that sort of stuff. It obviously wouldn't make a difference in the final results, regardless of what you did. So let's go ahead and set everything. So we're gonna do self.image size is our image size. Our self.patch size is our patch size. Self.inChannels in chans is in channels, and self.embedDim equals embedDim. And let's kind of do the math ahead of time, just so we know that what we're doing with the convolution is indeed what we're going to end up with. So what we have is a 224 by 224 picture, right? So if we do print, let's just take one of the dimensions. We're going to take 224, and we're going to divide by 16 because each of our patches are of size 16, which means each patch, if we do python model.py, we'll have 14 patches, right, along each dimension. And that's the key idea. If you have 224 pixels and each patch is 16, that means you'll end up with 14 patches in each dimension. So that means our total number of patches is going to be this squared, right, because it's a square. So we can square it up, square. So we should end up with 196 patches when we're done. Now the figure that I showed here is obviously a little bit misleading, right? I only drew 3 of them here, a 3 by 3, but that's basically the idea. We have 224 pixels. We divide them by 16, and so that means we'll end up with 14 patches in each dimension, and so that means we have 14 squared patches in total. So we have 196 patches, right? As you see right here, 196 patches. And so let's go ahead and make sure we get exactly that same result when we implement it. Okay, so how we're going to do this is we're going to do self.numpatches, right? Numpatches is going to be our image size divided by our patch size, integer division, squared. And we're just storing this in here for future use. So you'll see where that comes in later. And so first we have to do our projection layer, right? Proj is nn.conv2d, regular convolution. And our in channels is going to be in channels, right? How many are we expecting to get from the image? Our out channels is going to be our embedDim. And this will again make more sense later, but our final goal is to represent every patch as a vector of length 768 or whatever the embedDim is, right? So every patch needs to be represented by a vector of length 768. So that's all we need to do. We're going to do out channels is our embeddingDim. And again, you'll see exactly how that works out in a bit. Our kernel size is just going to be the patch size that we want. So this is us using a 16 by 16 kernel, extracting 16 by 16 patches from our image. After we do that, all we need to do is we can write our stride is also our patch size. This will ensure that as our kernel is moving over, it's a 16 by 16 kernel, it moves over 16 every single time in both the X and Y direction. And this ensures that our patches are not overlapping. You could also have overlapping patches, but I don't think in the case of the vision transformer, there was any sizable or any meaningful gains from doing something like that. So there we go. And then finally, we will add in an extra term here, bias equals true. Do we want to have a bias on this convolution? Typically we do. In some implementations they might not, but there we go. Bias should be bias. There we go. So now let's go ahead and check. What we're going to do is pass, and my bad, this is just patch embed right here. Then we're going to do PE rand. We're going to pass our data into our thing. All right, so all we need to do is if we print x.shape, just making sure everything loads correctly, which of course it won't because I forgot my super, patch embed self dot init. Go. Now it should work. So there's our data coming in, and our goal is to patchify this up using our convolution. So let's first go ahead and do that. So we're going to do our x is going to be self.proj x. And so if we print x.shape, and let's print it before and after so it's clear, print x.shape, what we see is we go from a 4 channel by 3 by 224 by 224 to batch size of 4 by 3 channel by 224 by 224, right? So that's our input. To a batch size still stays a 4, but our 3 channels have now become 768, and our 224 by 224 became 14 by 14. So we're starting to see that 14 show up. What we have here is 14 by basically a 14 by 14 image with 768 channels. And that's the key idea. And this is all that patch embedding module did. There's again a bunch of ways we could have done this. The other way, right? The other way would have been we could have used that patchify function and basically created each patch would have been 256 numbers, right? There'd be 256 numbers in every patch because it's a 16 by 16. Then we could have had a linear layer to take our 256 numbers here and project it up to the 768 that we want. And this operation with the linear layer and the projecting is exactly the same as using the convolution because, like I've talked about before, convolutions and linear layers are exactly the same thing. There's no difference between how a convolution and a linear layer works at all. So this is it. So this convolution layer is doing exactly what that linear layer would have done. It just does the patchification process for us too. And that's the key idea. So there we go. We now have our data, but we need to reshape it, right? Because as we know in transformers, our typical shape for a transformer model, right, for data is batch size by sequence length by embedding dim. What we have right now is batch by channels, and the channels is our embedding dim in this case, by some height by width, right? So let's go ahead and first do a flatten. So we're gonna do x. Let's get rid of u. Don't care anymore. X is x.flatten, and we're gonna flatten everything after the second dimension. So, I don't need u. There we go. So now we have a batch size by our embedding dim, 768, by our number of patches. We have 196 patches. But we need batch by num patches, or sequence length, by embedding dim. So now we just have to transpose these 2 dimensions. So we can do dot transpose, 1, 2. And we end up with what we want. We have a batch size by our sequence length, which is just the number of patches, by our embedding dimension. And so this is the entire patchification process of our image, just using a simple convolution. Again, we could have written a patchification, we could have written a module that had done this. We could have cut our images up and then used a linear layer, but the convolution does exactly the same thing, just in its own way. But numerically, it'll give you exactly the same results. Good, so this is our patch embed. Now that we've kind of understood a little bit about how we're doing this, now it's time to talk a little bit about why we're doing this, right? So what's the entire point of this? A convolution, as you can imagine, what we had just done, right? The entire patchification process, a convolution on its own are local operations. It tells you something about this location, something about this location, something about this location, dot, 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 right? It tells you something about every single location because they're local operations where they're trying to extract features, right? They're trying to extract features from small parts of the image. The thing is that when we do this operation and we're actually convolving our filter over an image, the neural network has no way to learn how something like the top left part of the image is related to the bottom right. And so this lack of a global comprehension of the image is exactly why convolutions fail in some types of tasks that require that. So what are some tasks that require that? A good example is something like image captioning. So in image captioning, what you're trying to do is take a picture and write some text describing it. Now, if you want to describe a picture, you need to somehow understand the full context of the image, kind of everything that's going on. And so having a global view of the image is crucial, rather than kind of looking at little parts of it and trying to decipher what may be going on in that part of the image. On the other hand, let's say you're working with, like I did a project with the civil engineering folks, and they had a project about looking for cracks in maybe your cement or something like that. Cement and all these kinds of things there's a lot of texture and there's roughness and stuff like that. So you're trying to do a texture extraction problem in that case. Well, if you're trying to extract information from textures, convolutions are perfect for extracting information from textures, and that is a very fine-grained detail kind of problem, right? So you're trying to look for small details in an image. And so what you use kind of depends on what you're trying to solve. If you're trying to get fine-grained details, then convolutions might work for you. If you are looking for kind of a global view of an image, then vision transformers might be the one for you. Now, a vision transformer will probably perform similarly to a convolutional neural network, even on fine-grained details, given that the model is big enough, but you might be able to get away with a lower parameter model just using convolutions, right? So that's a key idea. Now, how do vision transformers give you a global view of the image? Well, think about what the transformer is doing. The attention mechanism that we're going to implement later was in the case of language, how is every word related to every other word? So you have this pairwise relationship of the relationships between the different parts of the sentence. In this case, for the vision transformer, we're going to have a pairwise relationship of how is every part of the image related to every other parts of the image. And that will include how is this patch related to neighboring ones, but it's also going to learn how is this top left patch related to the bottom right patch. And that gives you that global understanding of all the parts of the image in one go. And the cool part is we get to do it in parallel because the transformer is the attention mechanism is a parallelized operation. So those are just some kind of intuitive things to keep in mind. But now that we have this part done, the patch embed, this is it. This is the novelty of the vision transformer. Now that we have this done, everything else is going to go, I can go a little bit faster through it because I already assume that you know a little bit about transformers. Again, just take a look at one of my previous videos on the attention mechanism if you are unsure about this, but let's go ahead and do it. So for the remaining part of the vision transformer, what do we need? Let's just look at the paper. We need a multi-head attention and we need a multi-layer perceptron. So, okay, let's go ahead and do that. We're going to do first class self attention encoder, right? It's an encoder self attention because this is a bidirectional model. We can have like this patch can look into quote unquote future patches, but really just later patches. And then the future patches or later patches can look into the past. So it's a bidirectional model. Each patch can look at all of the image. There's no causal anything here. So that's why we can use a encoder self-attention. And this self-attention is no different than any other self-attention that we have done. So what we're going to do is let's call this our embedding, EMB. Even though I have done this, I do want to make sure that I am at least helpful for someone that's new to all of this. So we're going to just step through the shapes a little bit. So we're going to do our attention. It's going to be our self attention encoder, and we'll see what that looks like when we actually start using it. So init, just like always, we're going to give it a self. Our embed dim is going to be 768. That's what we decided. That's what we're going to go with. And then we have our number of heads, right? Is going to be 12. Attention P, this is going to be our dropout probability if we want to have some dropouts. So this will be dropout on the attention mechanism, and then we'll have a dropout on the projections, right? So on the final multi-head projection. So there we go. And then fused attention, right? Or we can call it flash attention. It's going to be true. And so I'll have both options in here. We'll either implement attention ourselves or use the faster flash attention, right? So we'll see what that looks like in a bit. Let's go ahead and save all of these things as methods and just store some of the stuff that we need. So num heads is going to be our num heads. And then self.head dimension, right? Because we are doing multi-head attention, is going to be our embed dim that we have here divided by the number of heads, right? So there we go. How many our head dimension is in multi-head attention. Again, let's just look at the picture real quick in case y'all need a quick reminder. Multi-head attention is, instead of learning one attention matrix, we're going to have a bunch of them, right? We'll have a bunch of them. Oh, this picture is actually incorrect. I will fix that. We'll end up having a bunch of them. And when we do that, we're basically going to have to cut our 768 embedding dimension into 12 chunks of 64. And then on each of those 64 embeddings, that 64 embedding dimension, we're going to compute an attention matrix and then produce the output. So let's go ahead and do that. This is our head dim, so that'll be 64 in this case because 768 divided by 12. Then we have self.scale. This will just be a scaling factor that we'll use later. That's going to be self.head dim to the negative 0.5. right? So we just have our scaling factor. This is to normalize the variance part of the potential variance growth of the dot product. So there we go. So there's normalization. And then self dot flash attention is flash attention. So there we go. So let's go ahead and define all the pieces that we need. We can do self.qkv is nn.linear. There's actually a couple ways you can do this. You could have, actually, let's just stick to the way I normally do it. Even though my implementation online is different, it doesn't matter. So nn.linear, and it's going to be embedDim to embedDim. And then self.k is nn.linear, again, embedDim to embedDim. And then self.v is nn.linear, again, embedDim to embedDim. And then our final self.proj, right, projection at the end, it's going to be, again, nn.linear embedDim to embedDim. So there we go. We also need a quick dropout, so we're going to self.attention drop is nn. Self.attention drop is going to be nn.dropout. And in this dropout, we're going to use the attention p. And then we'll also need another dropout at the very end. So this will be our proj drop. Again, nn.linear, or sorry, not linear, dropout, proj p. So there we go. So those are all the layers we need. Standard attention setup. Right, so let's go ahead and do the rest of it. Forward, self, x. And so we know our data coming in is going to be batch size by sequence length by embed dim, this x dot shape, right? Sequence len, comma, embed dim. There we go. So let's go ahead and pass it in. So into attention, we're going to pass in our embeddings, right? The thing that came out of our patch embeddings. So there we go. And so if we just print out x.shape again, just to remind ourselves exactly what's going on, we should see a, like every single time, super self attention encoder dot init. There we go. Ooh. There. So we got our batch size by our sequence length, quote unquote sequence length. It's really just our patch size or number of patches. And then our embedding dim. So we're good to go there. So let's pass our x into QKV and kind of remind ourselves of what some of these operations were. So first off, we will have, let's do q. So q is self.q. We're going to pass an x, print q.shape. So remember, q's shape will be identical to x, right? So nothing changed. But q, this query vector or matrix, is a projection of the original x, right? It's a projected matrix. So there we go. We now have our data, but we want to do multi-head attention. And so the first step in multi-head attention is take the embedding dimension and split it up by number of heads by the head dim. So we already computed that, so we can do dot reshape. We're going to leave batch size and sequence length alone, but our embed dim we're going to split into self dot num heads by self dot head dim. We could have also done it the other way around, but that's fine. So all we did is take the 768 embedding dimension and we separated it up into 12 heads, each with 64 embedding dimensions, right? So there we go. That's our setup. And now what we want to do is parallelize the QK transpose, all the operations that we're about to do. We want to parallelize it along the batch, like always, and the head dimension, which means we need to take the head dimension and just move it behind our sequence length. So let's go ahead and do that. We can do dot transpose, and we can just swap the middle two dimensions, right? Just doing a simple transpose will do that. And you'll now see that we have a batch size by number of heads by sequence length by head dim. So again, the intuition, or the way you should think about this, is I have 4 samples. Each sample has been split into 12 different heads that we are going to parallelize over. So that's 12 heads. And then we have each head has 196 time steps, or number of patches in this case. And then each patch is represented by a vector of length 64. So we could actually also flatten these two dimensions, like make it 48 by 196 by 64, but PyTorch will do that for us already, so we don't need to worry about doing that ourselves. So we have our Q, which means we just now need our K, and we need our V, right? QKV, which means we're going to pass Q, K, v, but everything else is the same, right? That everything else stays identical. And so now let's just do our simple attention formula, right? So first of all, we're going to do if self dot flash attention, right? So if we're using flash attention, then we're using the scaled dot product attention, which is significantly faster than actually just doing attention yourself, because it has a nice fused kernel that does the matmuls and the softmaxes at the same time in the GPU without a bunch of extra transfers between like the host memories. But either way, so we can do x is equal to f dot scaled dot product attention. It's built right in. And to scaled dot product attention, all we do is give it q, kv, and we give it our dropout p is going to be self.attention p. And we'll do that if we're in self.training. Otherwise, it's just 0, right? So if we're in training mode, then we can use our attention p. If we're not in training mode, then we don't want dropout, so it's 0. So this is if we're doing flash attention. And if we print x.shape at the end, right, we should get our attention drop. Let's see here. I need to actually save self.attention p as a variable. Let's do that. It's equal to attention p. There we go. So we got our output, right? There we go. That's the output of flash attention. Let's also do it without flash attention, just so it's clear. So we know the formula for attention. Let's remind ourselves real quick. The entire formula for attention is, here we go, QK transpose, right? So QK transpose is going to learn how is every time step, in this case, every patch, right? Every patch related to every patch. We'll learn this attention matrix of how everything is related to everything, creating a sequence length by sequence length attention matrix, right? So let's go ahead and do that. So step 1 is to do QK transpose. So attention is going to be Q at K dot transpose, and we'll transpose the last 2 dimensions, right? So -2, -1. We need to transpose the last 2 dimensions because we're multiplying let's just check. We want to do a batch by number of heads by sequence length by embedding dim, and we want to multiply it, that's Q, by K, which is batch, by heads, by embedding dim, by sequence length, right? So we need to take this S and E on the K, on the keys, and just transpose them to become E by S. So there we go, that's our transpose. And then we also have to, like if we see in the formula, right, we have our normalization factor, divide by the square root of the embedding dimension. So we can do that. In this case, the head dim, so we can do times self.scale because I've already done it here and it's negative 0.5, so it's already in the denominator. If we take a look at our shape, attention.shape, right, we'll end up with exactly what you think. We have a, let's see here. We have, let's do, we have to turn flash attention off. Let's do flash attention is false, right? So we go into that mode and we end up with a batch size. So how many samples do we have by our number of heads of attention? And then we have a 196 by 196. How is every single patch in my image related to every other patch in the image? And so that's my attention matrix. How is everything related to everything else? And now that I have that, I can go ahead and apply the softmax to ensure that my attention values all add up to 1, so it becomes like a weighted average, right? So we can do attention is equal to attention.softmax axis equals -1, or actually not axis, dim, sorry. Dim equals -1. We want to do it along the rows. This will ensure that when we do attention, right, our attention matrix, as you see here, these are the weights that we want to weight our values by, right? So what I want to make sure is that I want 20% of value 1, and then 10% of value 2, and 40% of value 3, and then 30% of value 4. I want my vectors here, each row, to add up to 1. So it's kind of like a weighted average, right? So it becomes, if these did not add up to 1, it'd still work, but it wouldn't be as robust. They could kind of be all over the place, and it would be less interpretable because I don't exactly know kind of the exact proportionate relationship between everything. So there we go. We're just converting our raw outputs of attention, right? Whatever the numbers were from the dot product after they were scaled, and we're just converting them to probabilities. So it adds up to 1, just so it's clear. So there we go. We now have our attention. And then very simply, this is where we'll do attention is equal to self.attention drop. Attention, we're going to do our dropout here. And then X is our attention at V. And there we go. that will go ahead and produce our final output. We can do, oh, I already have x.shape, so we can take a look. So x.shape is, there you go, batch by number of heads, by our sequence length, by our head dim. And now that I've completed attention and the entire operation here, because these matrix multiplications are all parallelized over our batch and the head dimension, so they're only really happening on these last two dimensions. Now that that's happened, I just need to put the data back how I found it. So I need to retranspose these back. So the 196 is here and the 12 is next to the 64, and then I can flatten them so it's all back together. And so we can do that really quickly. We can do x is equal to x dot transpose 1, 2, right? So that's going to flip these two dimensions. And then once we do that, we can do dot reshape and just put it back how we found it, right? Batch size by sequence length by embed dim. And so then we can print x.shape. Oh, x.shape. And we're here now. So we're back to where we started, right? We started with this and now we're ending with it. So there we go. Attention is done. But if you again remember the head dimension, all the heads of attention were parallelized over. So we computed 12 different heads of attention, but the different heads of attention were just concatenated together at the end, right? Making my 768. The different heads have not had a chance to just get to know each other. So that's why we have this final output projection that will just let the heads get to know each other. So we can do that real quick. We can do x is equal to self.proj x, and then x is equal to self.proj drop x for a dropout, return x. And we are done. That is our attention mechanism. Now on to our multi-layer perceptron. This is very simple. It's just a stack of 2 layers. So we're going to do MLP, NN.module, definite, self, and then this is just going to have some stuff, hidden features, MLP ratio. This is like every other one. And then we have our MLP P equals 0, right? So like in every multi-layer perceptron, for most attention modules, it's basically a stack of 2 linear layers that goes from in features, not that in features. We're going to go from in features to n features times MLP ratio. So how much do we want to do that hidden size expansion factor? And then we'll go back down to in features and we'll have some activation function, probably the GLU activation function in between the two. So let's go ahead and do that. So super MLP self dot init. Oh, init, there we go. So self.fc1 is nn.linear, and it's going to go from in features to in features times MLP ratio, right? So there we go. That's our first one. And then self.activation function is nn.GLU, right? We're going to do the GLU activation. And then we'll also throw a dropout in here, right? Just for drop. One is nn.dropout, and this will be MLP P. So that's my stack of my first linear layer with an activation and a dropout. And then we're going to have one more linear layer and one more dropout. So it's going to be self.fc2 is nn.linear in features, or actually now it's going to go from in features times MLP ratio to in features, right? So we're going to go back down. So again, we're going from 768 to 768 times 4, which will be our MLP ratio when we set it. And then we're going to go from 768 times 4 back down to 768. So there we go. And we'll have one more dropout. Drop 2 is nn.dropout MLP P. There we go. Self X. This should be pretty straightforward. All we're going to do is just take our data and pass it through everything. So it's going to be x is equal to self.fc1 x is self.activation function x is self.drop1 x. So that's the first chunk, and then x is fc2 x is self.drop2 x, and then we return x, and that is our multi-layer perceptron completed, right? So very simple. Again, I'm slightly speed running through this because I expect that you've done this at least once before. If you haven't, just go take a look at those videos, but for now this should be fine. So we have our attention mechanism and our multi-layer perceptron. Let's give that a try. So this will be, let's say this is our attention out, right? And then we have our MLP is going to be our MLP layer, and then we can pass the attention output into our multi-layer perceptron. Looks like we're missing a couple things. So this needs to be 768, right? That's our embed dim. So let's set that as a default. 768 will be the in features. And then our multi-layer perception ratio is going to be 4, right? Just like that. Okay, still another bug. So I called this, did you mean no attribute FC? Oh, FC1. There we go. That's why we test, and we are done. So we can print here X. Actually, it's probably better just to print the model out because it's literally just a stack of 2 layers. And so you can see it's basically a linear layer that goes from 768 up to 3072, and then a GLU activation. We have a dropout, and then we go from 3072 back down to 768, and then drop out again. So no problem. So we have now completed all the different parts that we need for attention, right? So we've completed mostly everything, but we now have to basically put it all together. So one interesting thing about the transformer encoder, I'm actually not sure if there's much of a difference in how you do it, but in the vision transformer, they actually pre-normalize the data, then give it to attention, and then they do the residual connection afterwards, and then they pre-normalize, and then they do it again. In the regular transformer implementation, you will pass it into attention and then do an add in norm afterwards, and then you'll pass it into MultiLayer Perceptron and then do add in norm afterwards. Whether or not it matters is I'm not actually sure. So I'm just going to say it doesn't and just go with the standard implementation. Actually, it doesn't really matter. Let's just go with what they did here. Yeah, we'll just try to stick to the paper. So we're going to normalize, then do attention, then do a residual connection. Then we're going to normalize, then do attention, or then do our multi-layer perceptron, then do our residual. Again, I'm not totally sure if it matters, if how much the order actually matters, but let's try to stick to the paper as much as we can. And I think that's how we did it in my implementation too. Mostly just going off the top of my head right now. So, okay, so we need our encoder block, self, and what would this need? So we need flash attention is true, right? We're always going to use flash attention. And then we'll stick in our embed. Dim is going to be 768, as we set it. Our num heads is 12. Our MLP, oops, sorry about that. MLP ratio is going to be 4. Our, let's see, proj p projection dropout is going to be, let's just say 0. Our attention dropout is going to be 0. And our multi-layer perceptron dropout is again going to be 0. So there we go. So let's go ahead and do the rest of this. So just like always, super encoder block self dot init. There we go. And so we'll first do a norm one, and then dot layer norm, right? Standard layer normalization for our transformers, just regular layer normalization. Then we will have self dot attention is self attention encoder, and we just need to give this all the information at once. Embed dim is our embed dim. Our num heads is our num heads. Our attention p is attention p. There we go. We'll have our projection p is our projection p. And then flash attention is flash attention, right? So there we go. That is our self attention encoder. And then we'll have norm2, and then dot layer norm again. And in this layer norm, we're again just going to give it the embedding dimension, just like that. And then self.mlp is equal to mlp. And then again, this just has its own stuff. So its in features is going to be our embed dim. And then the MLP ratio is going to be our MLP ratio, just like that. And I think that's all it needed. MLP ratio, and then yeah, of course, MLP P is going to be our MLPP, right? That's our dropout probability. So we have gone ahead and put it all together. Right? That's a single transformer block, right? So we have our normalization, attention head, normalization, multi-layer perceptron. Now when we pipe the data through, we have to make sure we add in these extra residual connections, right? So let's go ahead and do that. So def forward, self x. And what we're going to do here is x is equal to self dot norm 1 x. We're going to normalize our data first. So again, we pre-norm the data, and then we do attention afterwards. Self dot attention on our right? We pass our normalized data through attention, and then we take the original x that we had and add it to itself, right? So we're going to do x equals x plus, right? X equals x plus, all this stuff, and that basically produces our residual connection. Now that we have that, we can also do x equals x plus self.mlp self.norm2 x, and we return x, and that completes one of our encoder blocks. So let's go ahead and test it. So the encoder block will get the output of the patch embedding, so we can get rid of all this. Let's call this our encoder block. And so our encoder block will get the embedding. And so we can print here the x.shape and just make sure this all works. Yeah, and there we go, right? So we got an output, so we should be good to go. All right, neat. So now that we've completed the encoder block, it's time to just kind of put this all together to produce our vision transformer. Now there's still one step that we haven't talked about yet, and this is where we're going to implement it. Notice that we don't just pass in our patches, right? See how there's image patches here, but we also have this CLS, extra learnable class embedding, kind of prepended to the beginning. So if you remember, right, let's ignore the CLS token right now. If you remember, our transformer is going to learn every context vector that pops out of the transformer, right, on the other end. It's going to learn how is every token related to every other token. So how is the first patch related to itself? How is it related to the second one, third one, fourth one, ... And then once we learn all those interrelationships, we then weight them by the values, right? We just do a simple weighted average of the context vector that pops out at this position, right? Position 1, let's say, whatever pops out here, is a weighted average of how this first patch was related to all of the other patches. So it's just a weighted average of the entire sequence, which is really neat. The thing is that at the end of our vision transformer, right, what we need is a single classification. Let's kind of think back a little bit to Roberta, right? So when we had done Roberta, we passed in tokens, right? We had a sequence, but we randomly deleted, right? Masked. We had the entire masking strategy. We just masked stuff out, and that was fine. And it was no big deal. We masked stuff out, and so we wanted to predict something at every single time step for the things that were masked. So for the time steps or the tokens that were masked out, we want to predict something for them, and that was fine. Now we want to predict one thing about the entire sequence, right? Or the entire image in this case, which means there's two ways we can do it. Either A, remember, each of these time steps represents how this patch was related to all the other patches. We can either A, take all of the outputs here, right? Take all the outputs and average them together, just directly average them. And then use the average context vector from the output of the transformer to predict our class label, what we want to do. So that's option 1, and we'll implement both of them. We'll do both a pooling method, but the other way is to use a CLS token. A CLS token is just a learnable token that we just prepend to every single sample, just like you see here. And when we do prepend this, remember, this CLS token is going into the transformer just like all the other image patches. So as far as the transformer is concerned, this is just another token that it needs to process, which means we're going to learn how is the CLS token related to the first patch, the second patch, the third patch, ... So how is the CLS token related to everything? And then the output context vector at the index of the CLS token, let's go back. The output context vector at the index of the CLS token, right here, right, whatever pops out on the other end, it's going to be a weighted average of how the CLS token was related to everything else. And why is this important? It's because it's a weighted average. Right? When we did the pooling method, talked about the pooling method earlier, and just do a simple average, an average assumes that every single patch is equally important, which probably isn't true, right? If you're trying to do a prediction of if something is a dog or a cat, you probably only need to look at the face to make that determination, which means you'd want your weighted average to say that the patches that's more on the actual animal itself should be weighted higher, and the patches that's in the background or around the animal should be weighted lower. If you do a simple average, everything is weighted identically, and then the results may not be as good because everything is identical, whether or not it is a patch for the background of the image or a patch for the actual animal. They're all treated the same. By doing a CLS token, it ends up being a weighted average and gives the model an opportunity to weight patches that are more important for the specific classification task higher, and then also weight ones that are not as important, like background stuff, noise, that sort of stuff, lower. And so again, practically there shouldn't be too much of a difference, but there is, I can't remember off the top of my head, but there is a paper that does see that the CLS token does perform some meaningful gains when you train it for longer or something like that. But either way, let's just kind of keep it at that. We have the CLS token, so that's what we're going to implement. We're going to implement both methods, both the pooling method and the CLS token method, just so you can see. If we go with the pooling method, all we do is average up the embeddings and then use that average context factor, pass it to a classification head to predict what is it. If we use the CLS token, all we have to do is chop off the single context factor here, which is a weighted average of everything else, right? Just chop it off or slice it off, whatever. And then use that again as for our classification test. So we're going to see what that looks like in just a second. So let's go ahead. I'm going to copy this first part here because it's just a lot of stuff that you don't want to watch me type. So there we go. This is slightly different from what I'm doing. So let's go ahead and get rid of y'all. And let's turn you to flash attention, because that's what I called it here, flash attention. Everything else should be good though. So let's go ahead and do super vision transformer self.init. There we go. So let's go ahead and implement our transformer. This transformer is going to look very similar to every other transformer out there. So let's kind of just go through that process again. I'm going to store here pooling is pooling. This is going to be, so this CLS here, this can either be CLS or it can be average in the way that I'm implementing it, right? So that's what we're going to do. And so we'll just do that check. We're going to do a assert self.pooling in, I need to stop doing that, pooling in CLS or average, right? Those are my two options. Now that we have that, let's go ahead and start putting our model together. So again, if you remember, the first step is the patch embedding. So let's do that. Let's go ahead and do self.patch embed is going to be our, let's see, patch embed that we already defined. And this just needs to get some of the information, like the image size is the image size, 224 in this case. Our patch size is the patch size. Our in channels is our in channels. And our embed dim is our embed dim, right? Embed dim. So that's all the important stuff. So there's our patch embeddings. Now that we have our patch embeddings, the next step is to do all this extra stuff here regarding our CLS token. Do we want to prepend a CLS token? And then also add our positional embeddings, of course. So here is another difference from what we had done in the Roberta implementation earlier. In Roberta, we use the sine cosine embeddings to do our, basically our training, right? We use sine cosine embed. Actually, in Roberta, we use learnable embeddings, as far as I remember. Yeah, we actually did use learnable embeddings. So we're going to be doing exactly the same thing here. In the attention is all you need paper, when we did the language translation implementation, we use sine cosine embeddings there. In this case, we're going to be using learnable positional encodings. So it should be very simple. Let's go ahead and do it. So what we're going to do first is we're going to do if pooling is CLS, right? So if we're using CLS pooling, then our number of tokens, right? Before we have 196 tokens, that's going to go into our model, right? 196 patches. But if we add a CLS token, that means we have 196 plus 1, right? We have an extra one. So our num tokens is going to be self.patch embed. And this is why in this patch embedding module, I went ahead and computed how many patches I had, because I know this is going to give me 196 in my current setup. So I can just easily access it like that. So we can do patch embed dot num patches, and we're going to add 1 to it because we have that extra CLS token. Else, right? Otherwise, our num tokens is just going to be self.patch embed dot num patches, right? So we don't have that extra one. So there we go. So first we need to define our positional information. So let's go ahead and do that. Self.pos embed. And actually, maybe the easiest way to do this is by following the shapes as we go forward. So let's do def forward self x, right? And let's go ahead and just write the forward function as we are actually going forward. So to do this, what we're going to do is, let me just double check. We are going to do x is equal to self.patch embed x. And let's print out the x.shape, just like that. And now that we have x.shape, we can go ahead and define it. So we can do VIT is our vision transformer model. Everything can be left as the default. And we can do VIT and pass in our random tensor. And we should get the output of our patch embedding. So it looks like we have a mistake forward. There we go. There we go. There is our patched up and reshaped data. So again, simple patch embeddings, nothing else. Took our 4 by 3 by 224 by 224 and cut it up into patches, transposed it, created this. So this patch embedding, before we pass it to the transformer, there are two things that we need to do. Number one, we need to concatenate our CLS token onto it if that's what we want to do. And number two, we need to add our positional information onto it. So let's just write a quick method that does that, just so it's cleaner. So CLS pause embed self x. We could have also just done it in the forward function, but that's fine. So step one is we're going to need to concatenate our CLS token on. So let's go ahead and do that. Let's define the CLS token. Self.cls token is going to be nn.parameter, right? So it's a learnable parameter. And for now, I'm just going to define this as zeros. We'll deal with the initialization later. So for now, it's just zeros. And this is a CLS token of size embeddim, right? Because this, if each of these patches, right, each of these things here, if each of these patches are of length 768, that means our CLS token that we just want to concatenate or prepend onto our patch embeddings also has to be 768. So there we go. We're going to create a 768 vector, just like we did here. Now, the thing is that our data, again, is in the shape of batch by sequence length by 768, which means that all I've done is create a vector of length 768. It would be convenient just to have some extra dummy dimensions for these, just so I don't have to do a bunch of unsqueezes over and over again, right? Just so our code's a little bit cleaner. So let's just add some dummy dimensions in here that will be the placeholder for the batch dimension. The sequence length is technically correct, right? Because this is one time step or one patch or one token, so sequence length of 1, and this is embeddim. So this is just some dummy dimensions that we've added in. And similarly, our positional embedding is going to be nn.parameter, and then this is going to be torch.randn. And what we're going to do is torch.randn, or actually we can define this as zeros as well. We're going to initialize all this later. We're going to do zeros. And what we're going to do is 1. So that's our dummy dimension for the batch dimension. And then how many possible time steps do I have in my positions? Well, in this case, I have already computed num tokens. If we're doing the CLS, then we'll have 196 of them plus 1. So 197 is the sequence length that I'll be passing in for every image. If I am using pooling, then it's just 196. We won't have that extra CLS token. So there we go. We now have our num tokens, and each token is represented by a vector. Each position is represented by a vector of length embeddim, so we can just directly add them together. So there we go. That is our positional information. So what we're going to do now is just take our data and apply the CLS token and the positional information to it. So x is equal to self.cls pause embed x. So step one is if, right? If our pooling method, so if self.pooling is CLS, then we're going to have to prepend our data with the CLS token equal. So let's do that. This is going to be x is equal to torch. Actually, let's break it up a little bit so it's clear. We're going to do CLS, or let's print CLS token dot shape, and let's not do CLS token. Let's do self.cls token dot shape. And let's also print x dot shape, just so you can see exactly why we're about to do what we're doing. So we have a CLS token that is batch size of 1 one time step of length 768. And our data is batch size of 4 by 196 by 768. For me to concatenate this, we want to concatenate on the sequence dimension, right? This one dimension here needs to concatenate onto the 196 to create the 197, which means I need to make the other shapes match. Our embedding dimension already matches. They're both 768. What I need to do is make the 1 a 4, or just the batch size. So we need to repeat or expand this. Basically, it just makes duplicates of our CLS token just 4 times in this case, right? So let's go ahead and do that. So we'll call this CLS expand is going to be equal to our self.cls token.expand. And this is going to be x.shape 0, right? So that's the batch size. And all the other dimensions should be left alone. And there's only 2 of them. All other dimensions should be left alone. So now we can do CLS expand.shape. And this will give us exactly the same thing as before. We've just repeated the CLS token, batch size number of times, so everything else works out, right? So all dimensions are the same, and we can now concatenate this tensor onto this tensor without any issue. So to do the concatenation, we can do x is equal to torch.cat, and we're going to concatenate the self.cls, or sorry, not self. The CLS expand onto our x. Simple as that. And we're going to do it on dim equals 1, right? Because we want to do it on the sequence dimension. So dim 0, dim 1. So we're going to do it on the sequence dimension. So there we go. We have now concatenated our CLS token on. And the important part is just to remember where you did the concatenation. It doesn't matter where. We either prepend it, so we do it before, or we append it, like we do it afterwards. It doesn't matter which side you do it on, as long as you know which side you did it on, and just stay consistent. So let's print out x.shape, and you'll see now we have our 4 by 197, right, by 768. So we have prepended our CLS token. Good. So now that we have that, we can go ahead and just add our positional information. X is equal to x plus self.pause embed. So we're going to add our positional information onto x. Again, we've already ensured that our positional information has the right number of time steps or num tokens in it because we've calculated that up here. Boom. There we go. So we've done that. And then we're going to do x equals self.pause drop x. So this is going to be a dropout on the positional embedding. So let's go and do that. Let's do it down here actually. Self.pause drop is going to be nn.dropout pause p. There we go. So typical to add some type of positional information or dropout on our positional information. So there you go. Mainly because we're learning these positional informations, right? If we had a non-learnable positional embedding, then we would not care about a dropout. Good. So that is our, we can now return this, return x. That will go ahead and prep our data for the transformer. So everything else should be pretty easy now. That's our data. We can see we just prepended extra zeros at the top here, right? That is our CLS token. Right now it's zeros. We're going to make them, we're going to actually initialize them in some meaningful way a little bit later. But for now, zeros is fine. Now that we've gone ahead and done this, let's go ahead and define our transformer, right? So we're going to do self.blocks is going to be equal to nn.module list. And this is going to be our encoder block, and this just needs all the information. So flash attention is flash, what did I call it? Did I not call it flash? I did call it flash. Flash attention. Oh, whoops. I need to be doing this up here. My bad, sorry about that. So yeah, flash attention is flash attention. Then we have our embed dim is our embed dim. Our num heads is the number heads. Our MLP ratio is our MLP ratio. The projection P is proj P. Our, what else is there? Attention P is our attention P. Our MultiLayer Perceptron dropout is our MultiLayer Perceptron dropout. And that's it, right? So I think that's everything. Let's check. Encoder. Yeah, that looks right. Okay, good. So we have our encoder blocks, right? However many of them. And how many do we want? We're going to do 4 blank in range depth, right? So depth is what I use to say how many transformer blocks do I want to stack on top of each other. we can go ahead and actually print out our model. So we should start to see a actual model come together. And it should look exactly as I'd expect. Oh, we have our patch embedding, we have our positional dropout, and we have all of these transformer blocks stacked on top of each other, right? We have 12 of them in this case because it is a standard base vision transformer. So all we're going to do is for block in self.blocks x equals block x. So we're just going to pass our data through all of these blocks. And so this should work out, and we should get the correct shape at the end. Okay, let's run you. Get rid of you. I might reduce the size of this if it takes, oh, okay, one quick. So there you go. That's our final output. No problem there. Now, if you do remember, if we take a quick look here, if you do remember our data, right, we actually don't have a normalization after the multilayer perceptron, right? I mean, so we have a bunch of these, right? We have 12 of these, and so in the final one, in the 12th one, our multilayer perceptron, we add our residual connection and we return it. So what we want to do is just go ahead and normalize the final output of the transformer encoder because we actually haven't normalized it here. If we had the norm on the other side, then it wouldn't really be as much of a concern, but right now we don't. So let's go ahead and do that. So we can define our norm real quick. We're going to do x is, or self.norm is equal to nn.layer norm. And this is just going to be our embed dim. And what we need at the end is our prediction, right? To actually classify what we want. So let's do self.head drop, right? Drop out on the head layer for overfitting. Head p, and then self.head is going to be nn.linear, and this is going to be from embed dim up to our number of classes. And so now here's the key. Let's go ahead and implement both the both methods. So first let's do the CLS method. If self dot, actually first normalization, x is self dot norm x, and then we can do if self dot pooling is CLS, then like we said, all we need to do is extract that one CLS token from the 197 tokens, because that one CLS token should now be a weighted average of the entire thing, right? All the patches in the image. So all we need to do is our x is going to be equal to x and 0 in this case. So a batch dimension, we'll ignore the batch dimension. So for every sample in the batch, we're going to grab the 0th, or the first index effectively. And that's because we had prepended it. If we put the CLS expand on the other side, right, then it would have been the last one, and this would have been -1. It doesn't matter, right? Just as long as you're consistent in what you're doing. Else, right? So if we're doing mean, then we're going to do x is equal to x dot mean, and let's go ahead and set it up. So pooling equals average, right? So we're doing average pooling. So then we can print x dot shape. Let's comment u out for now. So if we had done average pooling, then we only have, notice we went from 197 tokens, which had the CLS token, down to 196. So we only have 196 actual tokens in this data. And so we can go ahead and just average all 196 of those things together, and we should be good to go. So we can do x.mean, and we'll do dim equals 1, right? Because we want to do it along the sequence dimension. And we are now golden, right? So there we go. So we can print x.shape. We can take a look at the shape in both cases. If we take the average, it's 4 by 768 because we averaged all 196 numbers together and it collapsed that dimension. So that's gone. If we had done CLS, which is the default, it will be exactly the same thing, 4 by 768. But in this case, we index the CLS token. Other than that, it's exactly the same. Now that we have that, we can do we can do x is equal to self dot head drop, and then x is self dot head, right? X, and print x dot shape. So this will be our final head, and we can see we have 4 by 1000 because there's 1000 classes in ImageNet. And we can go ahead and return x. So that goes ahead and is the full kind of implementation of the vision transformer. There's one more step though that I'm just going to copy paste in because it's less interesting. It's the weight initialization strategy, right? So we can just stick that right here. And then we need to just do a self.apply self.init weights. So all we're doing here is we're effectively initializing our CLS token, positional embeddings, and all of the linear and convolution layers, basically everything. We're initializing all of our layers, all of our learnable parameters with a truncated normal. I've seen this both ways. I've seen people initialize as normal, and I've also seen initialization as truncated normal. Whether or not one leads to better results than another is, I'm not sure. So I just stuck to what I saw in Hugging Face, right? So let's just initialize with truncated normal. Truncated normal is exactly what you think. It's just a regular normal distribution. But in case there's some outlier, like you end up, I mean, it's unlikely, but if you end up sampling something large, it just truncates it between like a specific threshold. Though I can't remember the threshold off the top of my head. You can look it up, but there we go. That's the standard initialization strategy for our vision transformer. So now that we have a fully functional model, it's time to talk a little bit about some of the problems of training a vision transformer. And the biggest problem is overfitting. So let's just kind of skip to the end real quick and just give you an idea. So let me find, there we go. So I'll just kind of show the results and we can come back to it. So here we go. So when you train a vision transformer with little to no augmentation, even on a relatively big data set like ImageNet, which actually isn't that big, it's only 1 million images, but when you train on a reasonably big data set, I trained this model for 300 epochs, and we can see our testing accuracy tops off at about 67-ish%, which is pretty bad for most state-of-the-art models. So a training curve without augmentation just does not work well. And even if you use some light augmentation like random flipping or things like that, it still will end up not working out so well. So we have a little bit of a problem because we have this great model, and even on a reasonable data set, we end up with bad results. So how do we get this? So this is the training results with augmentation. And in this case, we end up with something close to an 80% accuracy, just shy of the 81% that PyTorch reports. So the data augmentation I'm about to show is inspired by a lot of the, so if you go to PyTorch's website and go to their weights, you can actually see here, they actually have these things called training recipes. So you can go to the link for the training recipe and you can see what did they do to get the results that they did. So what I've implemented is something close to their training recipe, right? So there's a lot of places that we need to improve upon, and so that's what we're going to be doing now. Because the model part actually is not that difficult for the vision transformer. So let's go ahead and write some utils. So in the utils, there's going to be a couple things that we're going to do. The main things is we need some transformations, and we actually need some transformations called CutMix and Mixup, which we haven't talked about yet, but it's fine. We're going to take a look at it now. So let's do import torch, or let's do from torch vision, import transforms. We need from torch vision dot transforms import v2, and so you'll see why we're doing that. There's basically another set like updated transforms, and it has some of the transformations that we need. Lets us avoid just having to implement too much of this from scratch. And then you can do from our torch vision dot transforms dot functional. We're going to import in our interpolation mode, so that's fine. And we're going to do from torch dot utils dot data import default collate function. So that should be fine for now. Okay, so what we're going to do is go ahead and start creating our augmentation. So what's the standard augmentation? Let's go ahead and set our ImageNet mean and standard deviation, because our goal is to train this on ImageNet. Like I've already trained it on ImageNet, but here you go. These are the standard ImageNet mean standard deviation normalization constants, right? So there we go. I'm just going to copy those in. So let's go ahead and write our training transforms first. We're going to do def train transforms. Image size is going to be 224 by 224. Our image mean is going to be the ImageNet mean by default. The image standard deviation is going to be the ImageNet standard deviation by default. H flip probability, right? So random horizontal flipping, we're going to say with 50% probability. And then we're going to do interpolation interpolation mode. Let's just do interpolation. It's going to be our interpolation mode dot bilinear, right? Standard bilinear interpolation. And then lastly, we have something called the random aug magnitude. And we're going to look at random aug in just a few minutes. And by default, we're going to set this to 9. So there we go. Okay, so first up is let's do some of the standard transformations that we want to apply. So let's create a transformation chain. It's going to be an empty list of just transformations. And the first thing we're going to do is random resize cropping. So this sounds like exactly what you think. We have images. So ImageNet images are not 224 by 224. We are going to have to actually reshape them. But there's two ways we can do this. We can either reshape them, or we can go ahead and grab a random patch of size 224 by 224 from our image. So we can do transforms dot or transformation chain dot append, and we're going to do from the v2 version 2, we're going to do random resized crop. And in random resize crop, all we're going to do is provide it the image size. So we want you to grab random crops of size 224 by 224. In the case that your image is smaller than 224 by 224, then it'll just grab the whole image and then get it. But there is a scale parameter here. So notice here in the random resize crop, we want a final image of 224 by 224, but we have a scale and a ratio. So it can grab basically any size of the image that's within 8% to 100% of the image, right? So it'll grab a random crop. Here we go, expects output size of a crop, each head, a square output size is made, provide sequence length. And so it'll grab a random proportion, basically a random dimension, any size between 8% and 100%. And then it will resize that small image, or whatever it may be, up to the 224 by 224 that we want. And so then our interpolation is going to be equal to interpolation. And then anti-alias is equal to true in case we're like upsampling past the Nyquist rate. So there we go. So again, the key idea here is in random resize cropping, and we need to add that parenthesis right there. Random resize cropping, grab a random crop that's anywhere between 80% and 100% of the image size, and then take that crop and then upsample it up to the 224 by 224 that we want. So this is a great way of basically grabbing different chunks of the image, right, in a quick way. Again, we could write all these methods, but why bother when PyTorch already has a lot of these things built in. So that's that. Now we're going to do if h flip probability is greater than 0, right? So if we're doing that, then we can do transformation chain dot append, and we're going to do v2 dot random horizontal flip with p equals h flip probability, right? So we're going to add that on if we want to do it. And here's the important part. This is the random augmentation. So let's pull up rand augment real quick. So we're going to do rand augment. Okay, so rand augment is a data augmentation method that was created. You can go read the paper for it, but the idea is very simple. What we want to do is have a bunch of different augmentations happening on our model, and we could manually do it, right? Or we can let PyTorch just randomly sample some different augmentations and apply them. So what you can see is numops, the number of augmentation transforms to apply sequentially, right? Random augmentations. And these are augmentations from like flipping, color jittering, it doesn't matter, all sorts of augmentations. And then we have our magnitude, which is the kind of the strength of the augmentations. And so by default, you can see that the number of ops is 2 and the magnitude is 9, and we're going to stick to the defaults. Okay, so that's the basic idea. Instead of me kind of doing some, I could easily sample some, make a huge list of all the augmentations PyTorch has, and then randomly sample some of them and then apply them. RandAug will just do that for us. So we're going to do if random aug magnitude greater than 0, 0 would have been don't apply anything. Then we're going to do transformation chain dot append, and we're going to do v2 dot rand augment, and we're going to pass in our magnitude is the RandAug magnitude, and again the interpolation mode is our interpolation mode. Good. So there we go. So what we've done now is basically take an image, a full image from ImageNet, grab a random crop of it and resize it to 224 by 224, potentially do a flip, right? Randomly flip it, and then apply, in this case, 2 different random augmentations to it with strength 9, right? So there we go. We're just basically using the defaults in this case. After that, we need to convert, right? We're still in pill images, right? Everything we've done so far are still pill images. We need to convert the pill images to a tensor. So that's very simple. Transformation chain dot append v2 dot pill to tensor. We're going to convert our image to a tensor. There we go. And then what we're going to do is convert our convert to a float 32, right? So right now, this tensor, this v2.pill to tensor, will basically be between 0 to 255. We're going to go ahead and just rescale it to become 0 to 1. So we can do that really quickly as well. Transformation chain dot append v2 dot to dtype torch dot float 32 and scale equals true will ensure that we'll like scale it between 0 and 1. So we're going to convert it to a 32-bit floating precision, and then scale our data down to 0 to 1. And now that our data is between 0 and 1, we can go ahead and apply our normalization to it, because the ImageNet mean and standard deviation assumes that the data is between 0 and 1. So we can do our transformation chain dot append v2 dot append v2 dot normalize, and we're going to normalize with the mean is equal to our image mean, and standard deviation is equal to the mean is the image mean, and standard deviation is the image standard deviation. So that is our normalization. And so all we need to do now is return transforms.compose. We're going to compose together all of these transformations into a single forward pass, just so it's easier for us. So transformation chain. So we can see what this looks like. We can do print train transforms, and let's just pass that in. So we can do clear this out, python utils.py. And there we go, right? This is our sequence of transformations. We're going to do a random crop, right, between these ratios and our scale. So basically what proportion, smallest proportion, largest proportion of the image that we can grab. We're going to do a random flip. We're going to apply 2 random augmentations to it. We could have done more operations. We could have done less. We could use a higher magnitude. We could use less magnitude. In this case, I just left it the defaults, so it's fine. We're going to convert our image to a tensor. We're going to scale it down to be 0 to 1. And then we're going to normalize our data. And it's as simple as that. So that is our training transformations. Similarly, we need our evaluation transformations. To do evaluation is pretty easy. Transforms. Image size is again 224 by 224. Our resize size is going to be 256 by 256. And you'll see exactly why we're doing that in just a second. Image mean is equal to ImageNet mean. Image standard deviation is ImageNet standard deviation, and then our interpolation, I just want to keep it the same, interpolation mode dot by linear, so just like that. So one interesting choice for inferencing, and I actually see this everywhere, is I guess it has to do with the fact that like when we're doing a lot of these augmentations, they lead to like maybe potential artifacting on the edges, right? Like if we randomly rotate something, you'll end up with the black border around the picture. So a typical thing that I've seen is that you will end up resizing your image not to 224 by 224, but to 256 by 256. So resize it to a larger image, and then do a center cut of 224 by 224. And by doing this, your model's basically, or you're basically passing in images without any potential edge artifacts, because the model is learned not to really focus on the edges, because there's always random stuff going on there when you're applying these types of augmentations. So maybe if someone wants to drop down in the comments about exactly why we do that, but that's my guess. So we're going to do transformations. It's going to be very simple, transforms.compose, and this is just going to be our v2.resize. So we're going to first resize our data, and we're going to do it to our resize size, with the interpolation as our interpolation, and again, anti-alias is true. So we're going to resize our image to 256 by 256, and then we're going to do a center crop, right? Center crop. So we're going to do a direct center crop of the image size that we actually want. So image size, there we go. Now that we've done that, we can go ahead, and the rest of it is actually identical to before, so I can just go ahead and copy it in. We're going to convert our image tensor, convert it to a float32, scale it between 0 and 1, and then normalize our data with the ImageNet mean and standard deviation, and we are done. Return transformations. But all these transformations that we've talked about so far are actually still not enough. Actually, your vision transform model still has a good chance of overfitting even with all of these transformations that we applied, which is why we now have to enable one more thing, and this is known as the Mixup and CutMix. And honestly, it's easiest to understand this through a picture. So Mixup, CutMix. Let's just pull up a picture here. Images. Yeah, I like this picture. Let's look at this. Okay, fine. So in Mixup, so first of all, here's our picture, right? Picture of a dog. In Mixup, what we're gonna do is take images and blend them together, which means this picture here, you can see it's kind of a blend between a dog and a cat. So this picture here, the label, remember our labels, right? Originally for the dog picture, our label is it's a dog or it's a cat. But now this picture is partially a dog and partially a cat. So in Mixup, you're actually blending the pictures together. In CutMix, you are basically creating like a, what do you call them? A collage, right? You're taking pieces of one picture and cutting it and putting it into another picture. So these are obviously much heavier augmentation methods than what we've talked about, because we're literally blending images together. But it allows our neural network to be much more robust, because in this case, right, in this picture here, we can see this picture is like 1/4 of it is a cat and the other 3/4 of it is a dog. So that means this is a 25% cat image and 75% dog image. And so that's what we're going to do. So this becomes a little bit more challenging, but let's go ahead and implement this. Again, we're not going to implement the actual Mixup and CutMix because PyTorch has done a lot of this effort for us. So what we're going to do is write a collate function. So exactly how does this work? So if you remember, our data loader, right, when we grab data, we grab a batch of samples, right? Let's say a batch of 64. And so typically our collate function in image classification, we don't really need to think about a collate function because all the images are the same size. So the default collator, which is right here, what PyTorch has, the default collate function, is sufficient. So you'd use the default collate function and you'd be done. But what we're going to do is this. Let's say we have some batches of images. So we are going to have, let's say, image 1, image 2, image 3, image 4. Let's say we have 4 images in our batch. What we're going to do is do Mixup and CutMix between consecutive images. And this is how it's already implemented, so we don't actually have to do anything, but we'll see what it looks like when we do it. We're going to do it on consecutive images. What that means is we're going to do, let's say CutMix for now, right? We're going to take a piece of image 1 and paste it into image 2. And then we're going to take a piece of image 2, paste it into image 3, take a piece of image 3, paste it into image 4, then take a piece of image 4 and paste it into image 1. And then we just need to keep track of what did we actually, like how much did we paste, right? So what proportion is the original image versus the new image. So let's see what this looks like when we actually implement it, because it makes it a little bit clearer. So we're going to do Mixup, CutMix, collate function. So this is going to be our new collate function. And we're going to have a Mixup alpha. And this is the alpha parameter from a beta distribution. So the method that we're going to use will basically sample what proportion should I grab from one image and put in the next one, right? Or what proportion should I blend these images together, essentially. And so it's sampled from a beta distribution. You can look it up. It's not that complicated, but you want to be able to do like a random amount every time, right? Like you want to, like instead of always doing 50% dog, 50% cat, you could do like, oh, right now I'm going to do 20% dog and 80% cat, or I'm going to do 70% dog and 30% cat. So you just want some randomness in how much you're either blending the pictures together or how much of one picture you're cutting out and putting in the other one. So let's go ahead and do that. So our Mixup alpha is going to be 0.2, our CutMix alpha is going to be 1.0, and our num classes is going to be 1000. So the 0.2 and 1.0 I just got from a, basically I just looked online for what did in the PyTorch training recipe, what did they use? they use these numbers, so that's what I'm going with. So let's go ahead and create this. So we're going to do let's do this MixCut transform is none by default. Let's just leave it like that. And we're going to do Mixup. Okay, we're going to do Mixup CutMix is just an empty list for now. And so we're going to do if Mixup alpha is greater than 0, right? Then we want to use Mixup. So how do we do that? We can do Mixup CutMix. And we're going to do dot append. It's going to be v2 dot mixup. And we'll pass in the alpha equals mixup alpha, right? Alpha, just like that. And we also provided the num classes that we're dealing with, right? So it knows how many classes there are, because you'll see why again later, why that matters. Next, we're going to do if CutMix alpha greater than 0. So now we're doing CutMix. Then we're going to do Mixup CutMix.append. And again, we're going to do v2.cutMix. So the reason I'm using the v2 modules instead of just regular transforms is because v2 had some of these more complex transformations already built in, so I thought we'd use it. So we're going to do alpha equals CutMix alpha. And again, num classes is our num classes. And what we're going to do is randomly decide, do we want to do Mixup now, or do we want to do CutMix now, right? It's basically one or the other. So in one batch, we might do Mixup. In another batch, we might do CutMix. You wouldn't want to do both, because then it would blend them and then it would cut one piece. It'd be too complicated, right? So you wouldn't want to do both. We just want to do one of them, but we want to randomly sample which one we want to do if both of them are available. So we're going to do if len Mixup CutMix is greater than 0. It doesn't really matter if there's only one, but whatever. We're going to do MixCut transform. It's going to be v2.random choice Mixup CutMix. So this random choice will randomly select one of these transforms to do in every forward pass. And so now we can write our collate function. Our collate function is going to take in a batch. Our data, right? Our data can just be directly collated. So we can do collated is equal to our default collate. And we're just going to pass in our batch, right? Just, again, they're just images. Just go ahead and collate them together. There's nothing fancy to do. And then we can do if mix cut transform is not none, right? So if it's not none. So if, obviously, if we had applied none of this stuff, then this would have stayed none. But now it's not none, because we actually have some transformations happening. So if it's not none, then we can do collated is equal to mix cut transform collated. So there we go. Again, this is following, they have an example in PyTorch of how to use these methods, and I tried to follow their method as close as possible. Return collated, return collate function. And that goes ahead and completes our Mixup and CutMix. Again, we could have implemented these methods individually, but this is fine, right? It's no big deal. The reason we picked a smaller alpha here is that if your images are too blended, so the larger alpha, you had the more it'd be to 50-50, like closer to 50-50% basically. The more they're blended, the tougher it is. You want your picture to be like mostly a dog, but some cat blended in, or mostly a cat and some dog blended in. So the model at least has something to learn. Otherwise, it would be too complicated. On the other hand, when we're just kind of taking one piece and pasting it into another one, we can be a little bit more, we can make the problem a little bit more challenging. So there we go. We have our collate function. Everything's ready to go. One other utility we're going to quickly write here is just being able to compute the TopK results. So basically, when we inference our model, and you'll see this all the time when you are looking at papers, especially for ImageNet papers, they'll have a top 1 and a top 5 accuracy, right? So top 1 accuracy is that your model got whatever the model predicted is the correct answer. And top 5 accuracy is whatever the model predicted, the top 5 things, like one of the things your model predicted, the top 5 things, at least one of them was the correct answer. So we're going to do def, we're going to write a quick accuracy function, output, we're going to do pass in our target, and we're going to do TopK. TopK is equal to 1 to 5. There we go. And this is pretty simple. We're going to do with torch.inference mode, right? So if we're computing accuracy, we're in inferencing mode. So there we go. We could have also done no grad, that would be fine as well. And so what we're going to do is we want to get the maximum k that we want to compute. So we're going to do max k is going to be max of top k. So in this case, it's basically saying that I want to grab the top 5 things, right? If we had set this 10, then it'd be 10, but we want to do it up to 5. And that also includes the 1, of course. So we're just going to do up to 5 and then just index for the 1. Okay, so now that we have that, we can do batch size is going to be target dot size or shape 0. Let's get the batch size as well, so we can store that. And so here's where one of the challenging parts began. Our targets are actually now batch by num classes. So let's actually go ahead and do maybe an example here. What's a good way to do this? Let's do it at the bottom. If name equals main, I should have made an example for this. Let's do our loader our data set is going to be image folder. And let's see, we're going to do from torch vision.datasets import image folder, right? That's what we're going to be using to load our ImageNet datasets. And we just have to give it the path to my ImageNet folder. So let's do, let's see, mount data drive data ImageNet train. Let's see if that works. Let's print out the dataset real quick. It's probably good to actually see how some of this stuff works, and actually verify that it works. Is this path correct? Or is my image? Okay, yeah, there we go. So we have 1.3 million images in my ImageNet folder. So there you go. And what we're going to do is our loader, right? Loader is going to be, and this is going to be image folder, and the transform is going to be, so we can apply that. Our train transform is going to be our train transforms, right? The thing that we spent applying here. So we're still going to do these transformations. Even though we're doing Mixup and CutMix, we still have these transformations happening as well. So you can see it's quite a bit of heavy augmentation happening on our images. So we're going to do transform is equal to train transform, and we can verify next. We can do sample equals next iter dataset. Let's print out the sample real quick just to make sure it does indeed work. And there we go. We have our sample and we have our class label. I'm also going to make this the test dataset, so it's a little bit, I think I called it test. It also might be called val. Okay, I think it's called val, so let's do that. Oh, I obviously don't remember what I called it, so let's just check. ImageNet, ImageNet, ImageNet. Oh, it's called validation. Okay, let's do that. It's just shorter, so it'll be a little bit quicker. Validation. Good. So there we go. We have our sample, we have our label. So what we're going to do now is our loader, right? So our loader is going to be a data loader, which I haven't imported yet. So we can do from torch.utils.data import data loader. We'll have our collate function, right? Collate function is going to be our mixup CutMix collate function with just the defaults, right? 0.2, 1.0, that's fine. And we're going to pass in here our data set, and our collate function is our collate function. So there we go. We have our data set, we have our collate function, and I think, right, batch size, let's say 32 for now. Okay, so by default, actually, let's go ahead and ignore that for now. We're going to do 4, let's do again. In this case, samples is going to be next iter loader. And this should be exactly how our image datasets always are, right? You're going to have all of these pixel values, so a batch of pixels, and you'll have these class labels. And right now they're all 0 because the shuffle is false, but we should obviously make this shuffle equals true. So there we go. We have all of our class labels, like what is the picture of the 1,000 things that it could be, and here are all the input pixel values that go into it. But keep an eye on the class labels. What we're going to do now is we're going to do our, let's see here. Okay, let's add our collate function back in. Collate function is going to be our collate function. Let's take a look now. Let's first see if this works actually. Okay, notice our class labels just changed. So this actually makes it a little bit challenging to tell exactly what's going on just because there's so many classes. So maybe we can do a slightly smaller data set. We can do the dogs versus cats. Yeah, let's do that. So let's just do it on the dogs versus cats data set really quick. Dogs versus cats. So again, let's ignore the collate function so it's clear. I just want to make this as clear as possible. We have dogs versus cats. So you're either a dog or a cat. So you're either 0 or 1, right? And we have our pixel values up here. Now, when we add that collate function back in, notice what happens to our class labels. We go from 0, 1s, right? Like we had right here. And we now have these proportions. We have, and actually one mistake here is we need to update our num classes here should just be 2, right? Because there's only 2 classes. So let's do num classes is 2 in this case. So that'll make it extra clear. There we go. So our image, instead of just being 0, 1, like it's a dog or cat, now you can see it's 80% one thing, 15% another thing. The next image is 15, 84. The next image is 0, 100, right? So it's, you know, fully a dog or a cat. 84, 15, yada, yada, yada. Right, so this is the important idea that I want you to walk away from, or take away from this. Instead of a picture just being a dog or just being a cat, it's now 80% one thing and 15% another thing. And you know, it's basically randomly. So you can see in this case it's different. So this time it's 50% one thing, 40% another thing, yada, yada, yada. Nice. So this is why I wrote an accuracy function here, because our accuracy, normally our targets, right, or you know, our labels, right, or the targets in this case, they're typically just a batch, right? It's just a index of what is this picture. What I mean by, like, is it a dog or is it a cat? In this case, your targets is going to be a batch size by number of classes. For every sample, it can be any proportion of a bunch of different things. So what we're going to do is if, right, and it will be in most cases because we're going to be training with CutMix and stuff, if our target, right, our label, remember the output, the samples I predicted that had the proportion, those are the labels now. Instead of the label being 100% a dog, the label is 85% dog, 15% cat. So if target.shape, or ndim, right, ndim is 2. If there's 2 dimensions, which means it's a batch size by the number of classes that it's kind of split between, then we're going to do is target is equal to target.max dim equals -1, and we're going to get rid of one of the dimensions, so we'll just index it for 1, right? So we just only want the second dimension. So the reason we did this is because we're saying, okay, this picture might be 85% dog and 15% cat, but we're just going to make sure that our neural network predicted that it was a dog because it was mostly a dog. So again, the accuracy metric is a little bit tough to do on the training set as we're training because we're doing these random augmentations that's messing up the labels, but this should work just fine. So we're basically saying that, you know, whatever the class label of the highest proportion is in this image, that's the class label we're going to treat as our quote unquote label for this picture. Even though it's not exactly correct, it's close enough for now. And what we're going to do is our values and pred is going to be output.TopK is just a function built right into PyTorch, right? So TopK, we want to do it up to the top 5 things in this case, so max K. Dim equals -1. So our output, right, the prediction of the model is going to be batch by num classes as well, right? So we're going to grab what are the top 5 indexes in every single sample in the batch. So basically, what are my top 5 predicted classes from this specific thing? So there you go. It's going to be dim equals -1 along each one. We're going to do largest is true, is so we can just keep the largest one, and then sorted equals true. There we go. So again, if we look at the, again, output.TopK is a method that's already built into PyTorch. So we're good to go there. Now that we have that, what we're going to do is remember our prediction. So our predictions, our TopK, this comes out as, and let's go ahead and create a random tensor here to test this. So our samples labels, right? Let's go ahead and do that. And then let's say our rand logits, right? Random output from our model It's going to be torch.randn. It's going to be some batch size, which I decided was 32. And in this case, it's going to have, let's go back to our, I'm just going to say this is 1,000. It's fine. It'll just have a bunch of extra zeros, but for now, just ignore it. We're going to do 32 by 1,000. So there's going to be 1,000 possible classes. And so we're going to compute our accuracy between our output, right? That's going to be our rand logits and our labels, right? Our fake labels. There we go. Or, real labels, but they're split up by the proportions. And so we can go ahead and print our pred.shape. Let's see if this works. There we go. So we have, and rather than just the shape, it's more interesting to know the label. So these are my top 5 labels, like predicted labels, let's say. I know it's all kind of zeros right now because there is no actual 1,000 classes, but it's fine. These are my top 5 labels for each single class or each sample, right? So these are my top 5 predictions. And what I need to do now is check, is one of these top 5 actually one of my correct ones, right? So there we go. Let's go ahead and do that. So we can do our prediction is currently batch by our max k, so 5 in this case. I'm just going to transpose it and it'll make our life a little bit simpler. So we're going to do our pred is just going to be a pred.transpose, and we're going to transpose 0, 1, print pred. Right, so all I've done is transpose my data just like this. So they're just column vectors now instead of row vectors for each sample. And so if we print our pred out actually and print out our, and let's make our batch size a little bit smaller so it's easier. Let's just do a batch size of, I don't know, let's do 8 maybe, just so it's clean. We're going to print out our pred and we're going to print out our target. And let's kind of take a look. Here is our predictions, right, of what each top 5 thing could be. Here are our targets. So there's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 things in our targets, and there's 8 things here as well, right? Our list for each one. So we just want to check, is this number, in this case 0, in this column? Because that would mean for this specific sample, right? If 0 was in this column, that means for this specific sample, it got one of the top 5 things was the correct answer. And that's the key idea. Again, we're for the next one, right? 0 again. That means for this specific sample, these were my top 5 predictions. If 0, the correct answer is in one of these top 5, that means we got one of them correct. And so we're just going to do exactly that. We're going to do correct is equal to pred target. Right, it's just going to be just a Boolean vector matrix that looks just like this of trues and false. In this case, everything is false because it obviously didn't predict anything correctly, but you get the idea. And then all we need to do is just loop through all the k values and just keep the k's that we want and just store that up. So we're going to do x is an empty list, and we're going to do 4k in TopK, or for k in TopK. We're going to do our correct k is going to be correct, and we're going to grab up to the k correct. Remember, this is already sorted, right? Sorted from largest to smallest. That's why largest. Sure, it's sorted from. So this is the most likely prediction, and this is the 5th most likely prediction. So we're just going to loop through and grab the top k things in this case. And once we have the top k, we can go ahead and flatten it up. That's fine. Top k. Oh. Right here. We can flatten it and then just add it up. Dot sum. We're just going to add it up, and we're going to make sure the we're going to make sure our d type is torch dot float 32, just so it's that way. There we go. So all we're doing is adding up. In this case, if it's just 1, then it's just one number, so it's not all that interesting. But if you have, let's say top k, let's say top 3, that means we would grab the top 3 things here, so 1, 2, 3, and so that would be in this case false, 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 and then you'd add it up and figure out, is it correct? Is one of these true? So if one of these were true, then you would have gotten a 1. Otherwise, it wouldn't be a 1. So we're just adding them up to find out how many of them we got correct, and we're going to divide it by the batch size, right? Just so we can get our actual accuracy. Ax.append correct k divided by batch size. There we go. And then we can just do a quick sanity check if len ax is 1. So if we only had one accuracy metric that we wanted, then we can just return the one number that's in there. Otherwise, right? Otherwise, we can return just x. And there we go. So all we're doing is just looping through and calculating the top 1 and top 5 accuracy. This method, we could have also used the torch metrics, but I'm not sure if torch metrics supports the this thing here where we have to find the max target. So there we go. We could have, I guess, done that before we gave it torch metrics, but it's fine. So that goes ahead and concludes our utilities, right? So we have gone ahead, recap, we've wrote some transformations. We then did some heavy transformations with these CutMix and Mixup methods. And then we computed wrote a top 5 accuracy metric. Okay, last part, the training loop. So I am kind of half debating. I feel like this training loop is not all that different from my intro to like the Hugging Face stuff. So I'm going to just kind of fast track through this because there's not too much to do. But to begin with, I'm not going to type all this out, so let's just copy it. Right, so it's just standard arg parsing, right? Nothing crazy. We just have a bunch of, all the standard training. We have our experiment name, our working directory, how many classes, how many epochs, warm-up epochs, and everything I said here, all the numbers you see here, came from the PyTorch training recipe for the vision transformer. So there we go. And our args is going to be parse args. Let's make sure this works. And I've gone ahead and saved here a submit.sh, so that will work. But for now, instead of accelerate launch, let's just do Python. So we're going to do bash submit.sh, and this should print out our arguments. So there we go. We have our arguments. So let's go ahead and do the rest of this. I'll have a slightly more complicated version in my Git repo. I'll do a kind of simple version right now. A lot of this stuff is actually not interesting. I feel like there's nothing to learn. So maybe I'll just copy a bunch of this. Let's just copy a bunch of it. Yeah, because none of this is stuff that you wouldn't be able to do very easily. All I've done is I have my path to my experiment, which is my working directory. So my working directory is where I save stuff, and I just have my experiment name. And then I initialize my accelerator like I always do to this path to experiment. How many gradient accumulation steps do we want? Because we want to train with larger batch sizes. And if you want to log to weights and biases. We then go ahead and initialize our weights and biases with all the kind of parameters of this experiment that I care about. And there you go. I load my model, right? So I go ahead and load my model there. I feel like in here, I included so we have this custom weight in it, but that's my default. So I'm just going to ignore you. And then I'm going to ignore you. I'm just going to assume that's fine. We then define our training data. So our train transforms, just like we had earlier, right? Our training transforms, our evaluation transforms. We have our train data set and our evaluation data set pointing to the ImageNet data set in this case. We then have our mini batch size, because if we're doing gradient accumulation, if we want a batch size of 64 over 4 accumulation steps, that means each batch is actually 16. So there we go. We have a mini batch size. We have our collate function with the mixup and CutMix, just like we saw earlier. We have our train loader, we have our test loader, and we have our loss function, right? So there we go. Now, one important part in our loss function is label smoothing. So again, in the recipe, they used a label smoothing of 0.11, I believe. What label smoothing is to help the model not be so confident. Let's think about it in the context of just regular image classification, like dogs versus cats. Normally, your neural network will just like predict like this is 100, like the target always, this is 100% a dog or 100% a cat. But label smoothing, if you do like 0.1, it'll always smooth things out a little bit. So instead of your label, the final target being just 100% dog, 0% cat, or 100% cat, 0% dog, it could become like 90% cat, 10% dog, or 90% dog, 10% cat. It helps the model, it basically regularizes the model a little bit by making the targets a little bit more of a soft target rather than a hard target. And it's just good for helping with things like overfitting and stuff like that. Just a good regularization technique. So they decide to use it here because like we're seeing, we're having to do a ton of work, right? All this effort here is just to help the vision transformer not overfit. Like we need a ton of stuff, and this is just another tool in our tool belt to pull that off. So now that we have all that, we can go ahead and define some of the stuff that we actually need. We have our optimizer. Optimizer is going to be, just like always, torch.optim.atom. Again, weight decayed atom W, because we again want to help with our, trying to regularize our model as much as possible. We're going to do model.parameters. Our learning rate is args.learning rate, and our weight decay, right, is going to be args.weight decay. And surprisingly enough, if we look at our weight decay parameter, we use actually a pretty large 0.1 magnitude for the weight decay. So there we go, weight decay. Let's go ahead and define our training scheduler. I just use a cosine scheduler like I do all the time, so we're just going to do that. So num training steps. How many steps are we training for? That's whatever the length of our train loader is, right? Length of our train loader. Times the how many epochs are we training, so how many iterations to the train loader, args.epochs, divided by args.gradient accumulation steps, right? So because my train loader is based on the mini batch size. So if I want a batch size of 64, but can only do 16 at a time, I need to make sure I scale my number of training steps by that, right? So there we go. That's our number of training steps. And then after our number of training steps, we'll also have our number of warm-up steps, right? So how many steps do we want to warm up for? Warm-up steps. And this is again len train loader, but instead of args.epochs, we're just going to have our warm-up epochs, because we'll be, I believe, warming up for 30 epochs, right? We're going to warm up for 30 epochs and train for 300. So there we go, number of warm-up steps. Now that we have that, we can define our scheduler just like this. Scheduler is our get cosine scheduler with warm-up. We want to do it on this optimizer. Our num warm-up steps is our num warm-up steps, and our num training steps is our num training steps. Simple as that. And so let's go ahead and prepare everything just like we do in every single training loop for accelerate. We're going to do our model, our optimizer, our train loader, our test loader, our scheduler. It's going to be accelerator.prepare. And then we're just going to pass in the same thing, our model, our optimizer, our train loader, our test loader, and our scheduler, right? So there we go. We have now just kept everything. And we just want to make sure our scheduler is registered for checkpointing, because I don't believe it does that by default. So we're going to make sure our scheduler is also saved so we can pick up from where we left off. So let's go ahead, just write a very simple training loop. We're just going to do for epoch in range. args.epochs. In my code that I have in my GitHub, I also have the ability to pick up from where I left off. I have that extra resume from checkpoints, so you can just take a look at it there. I'm just trying to give a general idea of what this training loop would look like, just so we can get something working. And so let's go ahead and do accelerator.print. There we go. It's going to be training epoch epoch. Right, so there we go. And let's just go ahead and store some stuff. So we're going to do our train loss is an empty list. Test loss is an empty list. And we're also going to store our train top 1 accuracy, our train top 5 accuracy, and then we're going to have our test top 1 accuracy and our test top 5 accuracy. So we're just going to have these lists that we're going to store stuff in. And now for the purposes of training, we're going to have a accumulated loss is 0 for now. Accumulated top 1 accuracy is also 0. And again, accumulated top 5 accuracy is 0. Right? So standard stuff for our setup for basically all these training scripts that I do. And then finally, we have a progress bar. Right, and this is going to be a per epoch progress bar. It's going to be tpdm range len train loader, right? So how many steps in our train loader, but we're going to again divide by args.gradient accumulation steps, because we only want to update the progress bar after a full accumulation is completed. And we're going to do disable is equal to not accelerator dot is main process. We only want to print the progress bar once on the main GPU. We don't want to print it out 16 times if we're training on 16 GPUs. We're going to throw the model into training mode. And now our training loop is basically every other training loop. It's going to be for images, targets. And remember, these targets now may not be just like what the index is. It could be our batch by our, batch by the number of classes, because they're soft targets, because our images could be blended via Mixup, CutMix, that sort of stuff. So for images, targets, in train loader, we can go ahead and do images targets equal images.to accelerator.device, and then targets.to accelerator.device, just like that. And we're going to do with accelerator.accumulate model. So standard accumulation method. We could have also manually done the accumulation, but that's fine. We're just going to use stuff that we have. Our pred is our model images, right? We're going to pass our data through our model, get our predictions. Our loss is going to be, just like always, our loss function between pred and targets. And the cool thing about cross-entropy loss, which is what we're using, right? Cross-entropy loss, if we take a look at it, you'll notice here that for our target, we can have either n, the batch dimension, or we can have an n by other dimensions. In this case, it'll be n by c, right? So our number of classes for our soft targets, because our target is no longer 100% dog, 100% cat. It's going to be like 50% dog, 50% cat, or something like that. And on top of the blending that's already happening from MixCut and CutMix, we also have a light amount of label smoothing happening to further smooth the loss, to make sure the model isn't overconfident in its predictions. Good. So this is going to compute our loss, just like always. So it does the hard stuff for us. So our accumulated loss, we can do plus equals loss divided by args.gradient accumulation steps. There we go. Then we're going to store we want to basically average up our loss over a full accumulation. So there we go. That's how we're going to do it. And then we're going to get our top 1 accuracy, and our top 5 accuracy is going to be equal to our utils.accuracy metric that we wrote, right? We wrote this accuracy metric that takes in a prediction, our pred, which came straight from the model, and our targets, right? Pred and targets. And then again, our accumulated, let's just copy this, so I have to type it again. I'm going to have this 2 more times. And this is going to be the accumulated top 1 accuracy. The accumulated top 5 accuracy is just going to be our top 1, top 5, scaled up, just averaged up by our number of steps, right? So there we go. And then now that we've done all this, we can go ahead and do accelerator.backward loss, go ahead and compute our gradients on everything. And then we're going to do if accelerator.sync gradient. So again, the sync gradients flag is what we could have actually used to manually do the accumulation, but it's completely up to us. If we are synchronizing gradients, if you are unsure about this, just go take a look at my Accelerate tutorial where we talk about all this stuff in some detail. But when we are actually syncing gradients, that means we're ready to optimize the model, actually do a step in the model. Before we actually update the model though, it's good practice to do gradient clipping, right? In case there's a bad sample or something like that, that will mess up your model. So we're going to do clip gradient norm model.parameters, and then do args.max grad norm, which I set to 1, right? So basically we're going to clip all the gradients of the model before we keep going. There we go. And now we can do optimizer.step, optimizer.0grad, set to none, right? So just a small efficiency thing. So we're going to set to true, and then scheduler.step. And we are golden. And now that we have all of this stuff, we can do a quick check. We can do if accelerator.sync gradients. So if we have sync gradients, that means we've completed an accumulation. So gradients only synchronize only when an accumulation is complete. And this is exactly what this accelerator.accumulate flag is up to. So when we have synchronized, then we can go ahead and do the rest of the stuff. So we've computed our accumulated loss, top 1 and top 5 accuracy, but we've only done that we've done this on every single GPU. But if we have multiple GPUs, we want to average up the accumulated loss across all the GPUs and average up our top 1 and top 5 accuracy across all the GPUs. So let's go ahead and do that. So our loss gathered is going to be accelerator.gather for metrics, and we're going to gather our accumulated loss. So all this is doing is it's going to grab the accumulated loss variable that's been accumulating in our loss, right? For every step in our accumulation, it's going to go ahead and grab them from all the different GPUs. So if we have 6 GPUs, then this is now a tensor with 6 values in it, and those values are these accumulated loss values. So that's it. It's just grabbing them from all the GPUs. If you're training on 200 GPUs, it'd be a tensor of 200 things. And we're just going to repeat this 3 times, right? So we're going to grab this for our loss. We're going to grab it for our top 1 accuracy, so top 1 accuracy. And then we're also going to grab it for our, top 5 accuracy, right? And to grab the top 1, we're just going to gather these. And so in my case, I have a computer with 2 GPUs, so this will return like a torch.tensor, and it'll be like a list of like, oh, it's like 10%, like 0.1, 0.3, or whatever. So that means it got 10% accuracy, top 1 accuracy on the first GPU, and 30% top 1 accuracy on the second GPU, but I'm just copying everything into the first one. So I have access to all the variables in one place, which means I can then go ahead and do our train loss dot append. Right, I'm going to go ahead and store torch.mean loss gathered dot item. Right, so we're going to go ahead and average up our losses across all the GPUs, and then just grab the value itself. Again, we're going to repeat this 2 more times. Top 1 accuracy, top 5 accuracy, and we're going to store it in our train top 1 accuracy and our train top 5 accuracy, just like that. So that will go ahead and be our basically our update. And now that we've done this, that means one of these accumulations have been completed, right? So we've completed a gradient accumulation and we got to the batch size we want, which means it's time to go ahead and just reset these back to 0 for the next accumulation. And also, when a full accumulation is complete, then we can go ahead and take our progress bar and update it by 1, right? That means we've completed 1 full accumulation. And that's basically it. That's our training loop. Our evaluation loop is exactly the same, so I'm just going to copy the rest of this. There's nothing different in evaluation. All we're doing in evaluation, same thing, we're looping through our data. And so this is a standard setup, right? We're going to train for an epoch, evaluate for an epoch, and just toggle back between the two, move our data. We're going to now compute our predictions without our gradients. And the important part here is, if you remember, on our evaluation data set, we're using testing transforms, and the test transforms don't have all of this fancy augmentations and cut mixes and all that stuff. Like, notice there's no collate function here. In the train loader we have it, in the test loader we don't. So when we're validating our model, we're not going to be doing all of this extra stuff, right? We're just going to do a very simple, like we saw in our utils, we're just going to take our picture, we're going to size it up to 256 by 256, cut it, and then just normalize it, and we'll be good to go. Center crop it and then normalize it. So just very simply, that's all it's going to be. We're going to compute our accuracy, right? This is very simple accuracy. And then we're going to gather everything across the GPUs, store them, average everything up, print it, and then log it to weights and biases. So nothing fancy, right? There's nothing happening here that we haven't done already. The key idea is just that when we are doing this, we're basically, the evaluation is going to be a much easier task than training. So we're training the model on a much more difficult task than just image classification. Like, we're still doing image classification, but we've added all this extra effort. Like, we've added a bunch of augmentations, which makes it challenging already. But then we added Mixup and CutMix, so our targets, the thing that we're trying to predict, isn't even this is a dog or a cat or a car or whatever. Now it's like, oh, it's 50% of a dog and it's like 60%, whatever, right? It's a mixture of images rather than just a single one, which makes it a significantly tougher challenge. And so this should probably work. Let's see, bash submit.sh. Let's see if it works out. Train transformations. So it looks like I missed that. Utils.train transformations. What did I call it? Oh, okay. So let's just make the names the same. So train transformations, and then we have eval transformations as well. Okay. Now let's give it a try. Find any other bugs in here. I'm sure there's a bunch, or not. Okay, it'd be shocking if there wasn't a bug. This is going to take a second to prep. Okay. I wonder if it's actually doing anything. Let's check. NB top. Yeah, this first GPU is getting hit really hard. Okay, yeah, training is happening. So we can see it started. It just takes a second to start. Now, obviously this is not helpful because we're only hitting one GPU and we're also not even using mixed precision, right? So let's go ahead and change our submit function to not be Python, but accelerate launch. So now this will hopefully work. It should hit both GPUs. Or when I was training it on the cluster, it was hitting like 16 of them, but that's fine. So we have, yeah, so we can see we have half as many iterations because, well, we have 2 GPUs now, so we get through the epoch twice as fast. This will again just take a second, but soon enough, it should start to actually utilize these GPUs. So yeah, it takes a little bit of time just to, oh, there we go, yeah. So much faster, right? So we're going 5, 6, 7, 8. It's going to go a little bit slower because I also have the OBS stuff running, but that's fine. We're hitting both GPUs. You know, it's actually being utilized. Awesome. So yes, so that basically concludes the coding part of this, right? So I know it was a lot, a little bit different than probably some of the other videos out there on YouTube on the vision transformer, because I wanted to specifically show how would you go about reproducing the vision transformer on the ImageNet dataset. It's pretty easy to fine tune these things, so I'm not going to really talk about that, but I wanted to just talk about specifically all the extra effort, which is all this stuff that you have to put in to be able to take this model that we wrote and actually reproduce it on the ImageNet task. So let's go ahead and recap the final results of this model, right? So we kind of talked about this. Something to keep in mind here. So this is, again, training with all those augmentations. Notice our training accuracy is significantly lower for most of training than our testing accuracy, right? And that's because our training the training task, the task we're actually training on, is significantly tougher than what we're validating on. Like, again, when we're training the model, it's all of these heavy augmentations. We have random augmentation, we have Mixup, we have CutMix, we have all this stuff going on. And that heavy augmentation makes our training task, right, basically computing the accuracy or the loss on the training task, significantly more challenging than doing it on the validation task. So we can actually take a look at, I believe I have the results right here. Yeah, so here we go. Here is our training loss. Oh, do I only have it for one of them? I guess I'll have to fix this. That's fine. Okay, I guess there's an issue with weights and biases. That's fine. Either way, that's basically the takeaway. So I trained this on a 4x100 GPU node. It took about 2 days maybe to get through 300 epochs, which isn't the worst. But either way, if you are looking to train a vision transformer from scratch, then this is kind of a great place to go. Or you can just go to Hugging Face, or you could go to the PyTorch recipe and just use it from there. This was mostly just an experiment on my end to see what does it take to train a vision transformer. And to my surprise, just training it was not enough. Even on a large data set with 1.2 million images like ImageNet, we had to do all this extra crazy stuff to actually get it to work. Again, the entire purpose of this video is not really as much about the vision transformer and more about doing masked image modeling, which we'll look in a future video, right, when we implement the masked autoencoder. So thank you everyone for, if you made it this far, I hope you learned a bunch. If you have any questions, drop it down in the comment section below, but I will see y'all in the next one.